Team dynamics refers to the ways team members interact, share information, and influence each other to reach a common goal. Think of a rowing crew. Each rower must sink their strokes, adjust force, and trust the coxswain's call. Psychological safety is the invisible cushion that lets members speak up, admit mistakes, or propose new ideas without fear of ridicule or punishment. Theoretically, these ideas draw from several streams. Social identity theory: people see themselves as part of a team group. Interaction process analysis: Bales, 1950, that categorizes behaviors into task-oriented and socio-emotional. Learning orientation frameworks: Argyris and Scone, which argue that safe environments enable double-loop learning. Scope includes any permanent or temporary group of 3 to 12 people, where interdependence matters, from product development squads to hospital surgical teams. Edmondson's psychological safety scale is a 7-item Likert questionnaire. 1 equals strongly disagree to 5 equals strongly agree. Example item: if I make a mistake on this team, it is not held against me. To test reliability, we compute Cronbach's alpha. Alpha equals k divided by open parenthesis k minus 1 close parenthesis times open parenthesis 1 minus open parenthesis. Sum from I equals 1 to k of sigma I squared divided by sigma t squared close parenthesis, where k equals number of items, sigma I squared equals variance of item I, and sigma t squared equals variance of the total score. An alpha greater than or equal to 0.80 is considered good for MBA level research. After reliability, we run an exploratory factor analysis, abbreviated EFA. Using principal axis factoring with a Varamax rotation, we expect one dominant factor, loadings greater than 0.60, that captures the safety construct. Confirmatory factor analysis, abbreviated CFA, can then test model fit, chi-square over degrees of freedom less than 3, comparative fit index greater than 0.95, root mean square error of approximation less than 0.06. To see how safety moves performance, we usually start with a simple linear regression colon. Performance sub I equals beta 0 plus beta 1 safety sub I plus epsilon sub I. If beta 1 is positive and significant, p less than 0.05, higher safety predicts better performance period. Mediation adds a middle variable, for example team learning L colon. Safety to L a paths. L to performance B paths. Direct effect C prime, total effect C equals a times B plus C prime. We test mediation using bootstrapped confidence intervals, 5,000 resamples period. Effect size for regression can be reported as f squared equals r squared divided by 1 minus r squared. Cohen's small equals 0.02, medium equals 0.15, large equals 0.35 period. For mediation, use k squared equals a squared b squared divided by a squared b squared plus sigma squared, or the proportion mediated equals a times b divided by c period. The input process output IPO model treats a team as a system. Input colon member abilities A, resources R, and psychological safety S. Process colon communication quality C, coordination Co, and conflict management CM. Output colon performance P and innovation I. A quantitative specification might be P equals gamma 0 plus gamma 1 A plus gamma 2 R plus gamma 3 S plus gamma 4 C plus gamma 5 Co plus gamma 6 CM plus epsilon. In simulation, we can assign distributions. For example, a tilde n of 3.05, S tilde uniform of 1 to 5, and run Monte Carlo runs 10,000 iterations to see how variance in safety shifts the distribution of P. Sensitivity analysis, Sabal indices, reveals safety's contribution to output variance, often greater than 30% in knowledge-intensive teams. Explanation, game theory formalizes the trade-off between cooperation and self-interest. The classic prisoner's dilemma payoff matrix illustrates why teams may withhold information. Cooperate versus cooperate yields 3,3. Cooperate versus defect yields 0,5. Defect versus cooperate yields 5,0. Defect versus defect yields 1,1. If safety is low, the defect, hide a mistake, becomes rational. Introducing a trust-building mechanism, for example public debriefs, changes the payoffs to 4,4 for mutual cooperation, shifting the Nash equilibrium toward cooperation. Network models view a team as nodes, members, linked by ties communication. The trust index for a pair I, j can be modeled as T sub ij equals the sum over k belonging to ni intersect nj of w sub ik times w sub jk divided by the product of the square root of the sum over k belonging to ni of w sub ik squared, and the square root of the sum over k belonging to nj of w sub jk squared. The cosine similarity of their connection vectors. Higher average T across the network predicts lower conflict frequency, negative correlation R approximately -0.45, and higher collective efficacy. Leaders can invest in workshops, coaching, or digital platforms that boost safety. A simple cost-benefit model. ROI equals delta performance times revenue per unit minus program cost, all divided by program cost. If a 6-month intervention raises team performance by 0.12 standard deviations, which translates to $200,000 revenue lift, and the program costs $40,000, then ROI equals 200,000 minus 40,000 divided by 40,000 equals 4.0 or 400%. A break-even analysis compares the marginal cost per employee, C, to the marginal benefit, B equals beta 1 times delta S times revenue. Sensitivity checks plus or minus 10% cost, plus or minus 10% benefit show robustness of the investment. Consider 2 fictitious tech squads, alpha open parenthesis, high safety close parenthesis versus beta open parenthesis, low safety close parenthesis. Data open parenthesis, n equals 50 each close parenthesis show alpha safety mean equals 4.3 open parenthesis standard deviation equals 0.4 close parenthesis comma performance mean equals 85 open parenthesis standard deviation equals 5 close parenthesis. Beta safety mean equals 2.9 open parenthesis standard deviation equals 0.6 close parenthesis comma performance mean equals 72 open parenthesis standard deviation equals 8 close parenthesis. A 2-sample t-test gives t of 98 equals 9.12 comma p less than 0.001. Cohen's d equals open parenthesis 85 minus 72 close parenthesis divided by open parenthesis 5 plus 8 close parenthesis divided by 2 close parenthesis equals 13 divided by 6.5 approximately 2.0, indicating a large effect. Regression on the pooled sample yields beta 1 equals 5.8 open parenthesis standard error equals 0.6 close parenthesis comma r squared equals 0.41. Mediation analysis shows 30% of the safety performance link runs through team learning open parenthesis indirect effecta times b equals 0.9 comma 95% confidence interval from 0.5 to 1.3 close parenthesis. These numbers illustrate how safety differences manifest in measurable performance gaps. Reliability calculation. Given item variances sigma sub 1 squared equals 0.8, sigma sub 2 squared equals 0.9, sigma sub 3 squared equals 0.7, total variance sigma sub t squared equals 3.5, and k equals 3, compute alpha using the formula above. Answer: alpha approximately 0.82 acceptable. Regression interpretation output. Intercept equals 50.2, standard error equals 2.1. Safety beta equals 4.3, standard error equals 0.7, p less than 0.001, r squared equals 0.36. Explain that each 1-point rise in safety raises performance by 4.3 units, holding other factors constant, and that the model explains 36% of variance. Design intervention, provide a data-driven plan. A. Conduct baseline safety survey, sample size equals 120. B. Run a 4-week pilot of Speak Up workshops. C. Remeasure safety, expect delta S approximately 0.5. D. Estimate performance gain using beta 1 from regression. Delta P approximately 4.3 times 0.5 equals 2.15 points. E. Calculate ROI assuming $150,000 revenue per point improvement and $30,000 program cost. These practice items reinforce calculation skills, conceptual understanding, and strategic application.